So dot plots and stem and leaf plots certainly have their limitations, as we've seen earlier. Histograms can be another way to view the data, which can be very helpful for large data sets. So let's revisit the data set for test 1. So rather than plot individual values with a dot or writing them out of the stem and leaf display, we're going to put these values in a bin, which is just a group of values that fall within a range of values. It might be easier if we sort the data first. Well, since I'm talking about grades, it might make most sense if the width is 10. So the initial process is called a frequency table. So my table would look like this. I would have 2 columns, grade on the test in one column and frequency in the other column. So I'm going to start with my first class, my first width of 20 to 30. These ranges again are called classes. So note that it appears the classes overlap because I'm going to have 20 to 30, then 30 to 40, 40 to 50. And so I know many of you are thinking, isn't there a problem there? What if the value actually falls on 30? Which bin does it go in? Does it go in the 20 to 30 range, or does it go in the 30 to 40 range? So we're going to use the convention that a class from 20 to 30 inches includes values that are greater than or equal to 20 and less than 30. So greater than or equal to the first value and just less than the second value. So a value of 30 would go into the next class from 30 to 40. So now I just count how many are in each class. So in practice we use statistical software to do this, which eliminates some of these initial tedious steps. So for instance, between 20 and 30, I've got one value between 20 and 30, it's 20. And then I have another value between 30 and 40, it's 30, so just one value. And how many values between 40 and 50? We have 2, and so on. So again, a histogram is just sort of a bar graph with these particular values. So let's make some observations. Just note that the first bin, from 20 to 30, we go up to 1 on the vertical axis. The next one is from 30 to 40, again is at 1. And then from 40 to 50, we go up 2. Notice that the widths of each bin are the same. Often software will allow you to display the values over the histogram. You know, often when we're doing histograms, we're really just trying to get a sense of the shape, and so the individual values within each bin aren't quite as important. But nonetheless, often software packages like StatCrunch, which was used to make this, will let you do that. Okay, so let's go ahead and look at all three compared, and notice how the shapes of these all sort of match each other, just in slightly different ways. You know, again, we would comment on the shape, center, and spread for each of these graphs, each of these displays of data. So just a quick note here, you know, while there's no hard rule about the number of bins or bin width regarding the histograms, you should have enough to allow you to get a feel for the data, right? So statistical software packages usually do a pretty good job of selecting an appropriate bin width just by default. So this does not include the TI-8384. Occasionally you have to manually adjust the bin widths on the calculator, and you'll be able to see that in another lesson. So unless the data set is unusually large, like in the hundreds of thousands, you'll probably want between 5 and 20 bins. So also look to see the cut points make sense. So we selected the cut scores here to hit the 10s in our example for test 1 because that corresponds to grades, right? 90 to 100 is an A, 80 to 89 is a B, and so on. So let's look at the 3 histograms here I'm going to graph. So this first one, we have a bin width of 30. So we have just 3 bins here. It doesn't really give us a good sense of the data. Here's the one we just graphed. I think this is probably the best looking one of the 3. And here's one with a bin width, I think, of 2 or 3. This is a little too granular for me. I don't really like looking at all those gaps within the histogram. It's a little blocky. It just doesn't give me a good sense of the data. So again, you sometimes have to manually adjust these bin widths within the calculator or the software package. So we can also re-express the frequency histogram as a relative frequency histogram. So notice the frequency table below. If we add another column and express each as a proportion of the total, sometimes this is expressed as a percent. We're just going to keep it as a proportion here. Notice the resulting histogram. So let's first talk about the relative frequency. What I do is I find out the total number of observations here. So I have a total of 26 observations. So how do I compute this relative frequency? I'm going to take 1 divided by 26. Similar for the next one, 1 divided by 26, and you'll get 0.038. And then 40 to 50, it's 2 divided by 26, and so on. And so here was our frequency histogram. Let's go ahead and convert this to a relative frequency histogram, and notice what we get. It looks the same, doesn't it? Only one thing changed on this. Let's look at these side by side. What do you notice changed on this? It's exactly the same shape. The only difference, right, is the vertical axis. We have one on the left is a frequency. We see counts. The one on the right is relative frequency. We see the proportions. So histograms are crazy important in here. We'll be using histograms to graph several data sets in here all throughout the course. So make sure that you are able to do this with statistical software or the TI-8384. And if you need help, we will have some help videos on how to do this with both.